Hi everyone, my name is mpyanev, a professional software engineer and a computer science professor at Fitchburg State University. Welcome to our first live lecture on operating systems and networking that take place at Fitchburg State University. Today we're going to talk about the basics of what operating system is, what is the purpose of operating system, its main components including the operating system kernel, and way more. If you just came across to my channel or you're some of my existing students, consider subscribing so you can see more videos like this one. Now let's jump straight to the live lecture. Okay, so now if there are no more questions about the grading and everything else, then we can start with the first lecture for today. Today we're going to keep it simple, it's not going to be too long. So today we're just going to get introduced to the OS, what are the different components. I will briefly discuss how operating systems are built, and used, and what are the important things when we're designing an operating system. Okay, so the first question that I would have for you guys is, I guess you know like quite a few different programming languages, right? Or at least you're familiar with them. So if you're building an operating system, what do you think is the best programming language to do that?
Sorry, repeat your question, please.
So if you want to create an operating system, let's say you're working in a company that is, you're working for Microsoft, okay? Windows haven't been built yet, okay? But it's 2024. And then you get the task, okay, you need to build an operating system. So what programming language are you going to use to do that, and why? What do you think is the best?
Operating systems.
Yeah, what's the best programming language to build operating system?
Operating system, I would try for Linux.
With so Linux is operating system, right? But what programming language would you use to build it, to create it? What do you think? Yeah, yeah. And there,
To hazard a guess, I would say sort of like SQL.
SQL. Okay. How about you?
SQL languages like C.
C.
Probably. Right.
Okay. Any other? C++? Any other? Okay, so I also agree with C or C++, okay. They are the most used ones for building operating systems. So why? Why is that? Why do we use C and C++? Okay. Yeah, exactly. You use those for embedded systems too, yeah. So in the embedded systems, you also have OS. It just doesn't have user interface, right?
Supports libraries which can be used to develop drivers.
Yes, true. Any other ideas? Okay, so yeah, you're all right. We're usually going to use C or C++ just because those languages are working directly with the hardware of the devices, right? This is why you would use them for embedded systems, because you don't want any complications. They work directly with the processor and with everything on the motherboard. Unlike, for example, let's say Java or Python, which nobody of you said Java or Python, which is good. They work one level up, right? And for that reason, when you're building operating systems, you're usually using C or C++. C usually use it for, let's say you want to build a bootloader. So the program that is going to boot your computer, and then you're going to install the operating system, right? In C++, you can build operating systems, yes, is currently the best one. But yeah, anyways, just wanted to see what you think, which is good. Okay. Okay, so yeah, operating system, as we all know, is the program that really connects the hardware of your device, okay, with the programs that you want to use, okay. So here I laid out some of the goals. So you should be able to execute programs with the operating system. It should be obvious obviously convenient to use based on the use case, and you'll see later, depending for what you need to build operating system, you have different requirements. For example, for the embedded systems, you don't usually need a user interface, so you wouldn't care about everything to be user-friendly. For, let's say, if you build like Windows, Linux, those operating systems that are for users, then you really care about how the user interface will look like. So we're going to focus on the design there, and so on. So, okay, let's see a little bit about that. Okay, so now, here you can see a typical computer system structure, okay? So as we said, we have a hardware, we have the operating system, we have the application programs, and we have the users. Those are the four elements that build a complete computer system, and you need to make sure that all of those work together in order to have a good system that is liked by the users. Okay, so here's how it usually works. Logically, obviously, the computer hardware is in the bottom level. After that, on the top of this, we have the operating system. And inside the operating system, then we have our application programs, which can be like text editors, browsers, you know them, you're all using computers, so you're familiar with that. And after that, we have the final users that can use those. Okay? Okay. So, as I said, when you're dealing with operating systems, there are really 2 points of view. One point of view is from the user perspective, and the other point of view is really from the system perspective. So, as a user, what would you want in an operating system? Let's say you're a user, what are your requirements for operating system? What would you like from it?
Ease of use.
Ease of use? Yeah. Okay, good. Anything else? Good performance? Yes. Okay, so as you also can see, users really don't care about resource utilization, right? So when you go, I mean, if you're not a professional software engineer and you don't go to fix the system or something like this, you really don't care about this. You just want to go to your computer and you just want to use it. You want it to be fast. You want everything to work great, and it doesn't matter for you anything else. Let's say if you work on a workstation, right? So there are, for example, some computers that are accessed by multiple people. So there, if you're a system administrator, you might care about the system to still run fast, no matter how many users are logged in, right? So this is the only case where you are going to care a little bit about the resource utilization. But okay, this is from the user point of view, right? Now let's see from the system point of view. What do we want? So from the system point of view, let's say when you're building an operating system, you want two main things. You want to be sure that you're allocating the resources properly. So every computer has what components? It has a CPU, it has memory, right? It has input-output devices like monitors, keyboards, mouse, external hard drives, and so on. So the first thing the operating system needs is to really allocate the resources properly so they can be utilized sufficiently. Let's say if you have a memory of 1 gigabyte, okay, you want to, and what I mean is RAM, right, like the active memory, you want this memory to be utilized in the best way. So you use it as much as possible while keeping the maximum speed for all the programs, okay? If you have a hard drive, right, you want to keep your files there and you want to have enough space. Also, when it comes to the processor, you want to process as many tasks at the same time, okay? And the second main purpose from the system standpoint is to really be able to execute the programs and in the background to prevent and solve errors. So imagine if you're running your operating system, you're just interacting with programs, and you start getting errors that you need to decide how to fix. It's not going to work, right? You're going to start hating your computer. So for that reason, you need the operating system to really fix those problems on the background without bothering you. Okay? Okay, so as you can see here, there is not a specific definition for operating system. So you cannot say, okay, these things are involved in an operating system. However, because quite a few systems have been built already, we have some routine in which we're building them, right? So when you start an operating system, you have a program that is always running on the background. Okay, so you can see your screen and so on. This program is called the kernel. Okay, so the kernel is everything that runs in the background and make the resources inside your device usable, so you can actually utilize them and run programs on the top of them. Okay, and we're going to talk a lot about the kernel, how it is built, okay, and how it can work really on the background without any disruptions. Now, another very important thing is that if you have control and if you're the provider that is building an operating system, then you have control over the device, right? So, for example, in the 90s, when Microsoft was initially created and they released Windows, they were actually sued because initially how they made Windows is that no other applications could be used there. So for example, if I install Windows, I can only use like Word, Excel, so third-party providers, they cannot build applications. Which means that by building the operating system, you can really create a monopoly, okay, and just accept certain applications. Of course, these days, this is illegal, right? But this is a proof that based on your operating system, you can, based on the operating system, you can manage pretty much everything above it, okay? Okay. So now let's start little by little review how an operating system is built and also talk a little bit about the computer hardware. Okay, so as you probably know, especially who of you have ever installed operating system on your own? Who has it? Okay, you have. Anyone else? Yeah? Who has installed their operating system? I know some computers, they are coming already with pre-installed operating system, and this is why I'm asking.
I tried actually.
You tried? Okay, good, good. Anyone else that tried to install operating system? Yeah? Okay, good. I'm asking because especially, for example, for me, when I was younger, okay, and the computers, they didn't come with operating system. So usually you would get your laptop and then you would look for a disk, right, for a CD with the operating system, yeah, for an image, and you would try install it yourself, right? Usually it's going to be a pirate image, so you don't need to pay for Windows and those type of things those days. But yeah, this is how it was. Now these days everything comes with already installed operating system. But why I'm asking you this? This is because if you ever got a computer that doesn't have operating system, the very first program that you see is the bootstrap program. Okay, so this is a program that is always in your computer, no matter whether you have operating system or not. And what this program does? So first of all, it is located in the ROM, which is the memory that you can read only. Okay, so this means you cannot overwrite this program. and that means that you can use it to install an operating system, right? So everything starts from there. Every device might have a slightly different Bootstrap program, and as I said, in most cases, it is written in C. Okay? You can see that it initializes all the aspects of the system. So with this program, even without operating system, you can use your mouse, your keyboard, your monitor, and so on. And yes, so this is how a complete computer system looks, right? So usually you have a CPU, you have some disks, right? So you need a disk controller. You have devices that are connected these days by USB. So you have a USB controller. And finally, for the monitor, you have a graphics adapter, okay? So we'll need to see in the future how each of those components are implemented inside the operating system. Okay, so now you have now operating system, you boot the operating system with your Bootstrap program. What's happening? So the first thing that is happening when you load the operating system is your kernel gets activated. So what was kernel?
Kernel is a startup program, like it comes every day.
Yeah, exactly. So this is the main program of the operating system that always works in the background. Okay? So you boot the operating system, the kernel starts running. Okay? So after the kernel starts running, you also get certain tasks or programs that are called system processes or system daemons. Have you heard about system daemons? You heard or not? No? Okay. So system daemons are programs that are not part of the kernel, okay, but are still supporting the operating system, okay? So what we want is that the kernel is really like a shell, okay? So nothing can access inside it. That way, nothing can penetrate within the core of your operating system, okay? The daemons, they are running outside of it and help the kernel to run and to interact with the other programs, okay? So this is very important. Now, you can see that right here, in order for an application to run in your operating system, you need to disturb your operating system by doing something, okay? And this is called an interrupt, okay? This takes the operating system from one state to another, okay? So let's say when you run a program, you send a byte from this program as an interrupt to the CPU. The CPU changes some of the tasks that it's doing, takes this byte and starts running this particular application that you want to run, okay? This is the idea. Now, when an interrupt happens, okay, it can happen in a few modes, okay? So you usually have a kernel mode and you have a user mode. So, for example, you know you have some programs that you want to access, let's say, your camera, and you get a message, can this program access the camera of your device, right? So in this particular example, the program is asking you, can I get access to the kernel so I can actually use the camera, okay? And when this happens, sometimes it asks you, sometimes it happens in the background. So when a program wants to use services from the kernel, this is called a system call. So it calls services from the system, okay? And I will show later how this exactly is done, okay? Okay, so as we said, in order for some program to run and the state of the operating system to change and something to happen on your computer, you need to have an interrupt, okay? So once an interrupt happens, okay, the interrupt points to the address in your memory, okay, where there are instructions for how this program is going to run, okay? So all the interrupts are located in an interrupt vector, okay? And from there, you can get the different addresses from your memory, okay, where the programs are located, where are those instructions on how programs run, and this is how they get executed. Now, what happens if we get an error? So in operating systems, if you get an error, it is handled by trap or exception, okay? So this is an interrupt that is caused by error in your system. So if you have some experience with coding, you know what the exception does when you're, let's say, you want to write software. Are you familiar with exceptions? Yeah? Okay. So if you're familiar, you know that, let's say in programming, exactly. So let's say in your code, you're expecting an error, something bad to happen. And you're like, okay, I don't want my code to fail if there's an error. I want something else to happen, right? I want to say what is going to happen and how this error is going to be fixed, instead of just getting the error and the system to fail. So what I'm going to do, I'm going to write, for example, in Python, I'm going to write try. I'm going to write the keyword try, yes. Then I'm going to write my code. And then after that, I write except. And I can also specify the type of error that might happen. And I would say, if this error happens, then execute the next code, which is probably going to fix the error, right? This is what you want to do. So in the operating system, it's exactly the same. You are having a lot of tries, a lot of exception blocks, and in that way, if an error happens, you need to predict for it, okay? So unlike the other applications, in operating systems, it is very important how you handle the exceptions, because you never want the operating system to fail or to stop executing and so on. You know that recently it became a very word spread issue with Windows. So they did, right? You heard about it, right? They didn't update, and the whole world got blocked because of that. Yes, and this is just because they did the update, I think, of some of the drivers, right? Exactly. And you know, these days the OS is getting updated automatically, right? You don't update it yourself. So when all the computers get updated automatically, then there was an error that was not handled by exception, okay? And the operating system fails. Or I think in that case, certain task from the operating system fails, so many computers around the world get down. All right. So now, once we already know what kernel is and how it runs briefly, right? Now we can talk a little bit about the storages, right? And after that, we're going to also talk about the CPU. How is it structured, the different types, and so on. Okay. So what types of storage are they? You can actually also see it from here, right? So what are the different types of storages? Okay. 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 RAM, good. ROM, good. So ROM is the read-only memory, right? Okay, nice. And RAM is the random access memory, yeah. Okay, so what is the difference between the random access memory, the RAM, and, for example, the HDD, the hard drive, or the SSD? What's the difference? They are very different. Do you agree with me? Okay, so in RAM are located the programs that are currently running, okay? In the hard drive or in the SSD, which is the electronic drive, right? The solid state disk. There are the programs that are not running, okay, but are on our device, okay? Which one is faster? Exactly. RAM is faster, okay. Which one is volatile and which one is non-volatile? Okay, I will say it like this. Which one gets erased when we switch the power off? The RAM, okay? While the hard drive, it doesn't get erased, okay? So there is very big difference, and those two, they are together on the same computers. Do we agree on that? So you have RAM, and you might have SSD, you might have HDD, okay? Okay, so yeah, the RAM, the random access memory, is volatile, okay? And in there, you get the information before sending it to the CPU registers, okay? So you can imagine it like this. I will actually show you a graph very soon. Actually, let me see if it's the next one. Not yet, but I will show it to you right now so you can get some idea. Okay, so this is how it works. Now, usually the register is the fastest thing that you have on your device. The register is when the program actually gets executed, okay? So before getting into the registers, all the programs that are running, they are getting into the RAM. And when they get executed by the processor, they get into the registers. For the cache, we're going to talk a little bit later. Okay, and of course, before they go into the main memory, which is the RAM, they are in either the solid state disk, hard disk, and before they were like magnetic disks, optical disks, and so on. Okay, let's get back. Okay, so once you have your program into your main memory, which is implemented by random access memory, you have two types of instructions that you can send to the CPU, okay? So those are either load. So if we do a load instruction, what that means? We want the CPU to load the program, right? Okay. Or we have the store instructions, which means that we want to take something that has been executed in the CPU and save it into our memory. Okay. So this is important. Now, so we talked about the random access memory, and now why? Okay, let me ask you this question. So we agree that the random access memory is way faster than the SSD or the hard drives, right? So why don't we just have random access memory? Why do we need to have hard drives?
Also storage.
Okay, storage, good.
RAM works as template, right? So
Okay.
until program execution in progress, it stores the memory, like it stores the data.
Okay. True, true. So why didn't we make the RAM to be able to store information, but at the same time to be able to, yeah.
Becomes effectively like temporary program specific data that doesn't need to be kept by a computer.
Exactly. So you don't, so in the RAM, you want to have resource allocation. You don't want to constantly keep things there because you want to add tasks, you want to remove tasks all the time. So you always keep it busy, you always keep it fast, because if it gets like overflowed or you keep tasks for too long, you might be able to do too few tasks. You want to optimize it, right? This is the idea. Okay, good. So yeah, and for this reason, of course, we need the other type of memory, which is the HDD or the SSD. So one very good thing about the solid state disks, that I think most of the laptops today have solid state disks, is that once the power switches off, they can immediately copy everything from the RAM, okay, and store it. So then when you turn the power on again, the very first thing that the solid state disk is doing, it takes that information that it copied immediately from the RAM, okay, and loads it. So that way you're actually not losing the information of your device. You can see specifically in the older computers with hard disks, if the power gets off, you don't save any information that you're working on, any tabs, nothing like this, okay? So this is something very good about the solid state disk. Another reason why we need different types of memory is because the faster the memory is, the more expensive it is, right? So for this reason, we cannot have terabytes and terabytes of RAM. Okay, we need something cheaper, or the manufacturers want something cheaper, so you can get actually cheaper devices, right? So those are the reasons. And you can actually see that here. Yep, so those are the main things with which we're choosing our storage. Okay. Now, here on this figure, we can say that everything under the solid state disks is non-volatile, while everything above the solid state disks is volatile. So the information can be lost if you switch the power off. Okay? Okay. Now, the other component that we need to talk about, except memory, is the input-output devices. Okay? So, usually when you're dealing with input-output devices, normally you would be looking for some drivers, right? So you would want a driver that works with this specific device, so you can actually connect it to your computer and use it, okay? Or with, let's say, your monitors, your keyboards, you normally have already the drivers built in your operating system. By the way, when you're connecting different devices, the drivers in most cases are getting installed automatically to your computer. Okay, so how devices are managed? Okay, so if you're using high-speed input-output devices, the information gets transmitted with speeds close to memory speeds, which means that you can directly use this information. For example, if you have an external hard drive, if it's a hard disk, it's way slower than if you have SSD, right? How this information gets transmitted to the computer? Okay, so you have a device controller, okay? And the device controller is responsible for transferring the information to your computer, okay? In order for the device controller to work, as we said, you need a device driver. What the device driver is doing, it is setting up everything needed for the device controller to work, okay? So when you connect your external device, first of all, you get a device driver that is setting up everything. Then the device controller starts transferring the information, and once the information is transferred, the device driver then tears down everything else. Okay? Now, in some cases, let's say when you are having a device that is transferring a lot of data, so it's going to be a lot of bytes transferred, a type of memory that you can have is called DMA. I think it was direct, let me see. Yeah, direct memory access, okay? So what this is going to do, instead of every time going to look for the data inside the device, when you connect the device, all the information from this device is going to be transferred to a buffer, okay? And this buffer is the DMA, okay? So since all the data is transferred to this buffer, if you want to access data, you're going to send requests to the device, and then the device will give an instruction to the memory inside your computer, and the data will actually get transferred from this buffer to your hard drive, or as you can see, cache, or the CPU. Let's say if you have a program on external device that you want to run, the program will get to the cache and directly to the CPU from the buffer. So you don't need to access it from the device directly. All right. So, okay. Now let's go to the most interesting part, which is the processor. Right? This is the heart of every computer. Do we agree on that? We agree? Okay. So there are two types of processors. You can see here they are single processors and they're multiprocessors. Okay. So in the single purpose processors, obviously you're having one processor, one core running a specific task. Okay. So I'll ask you a question. How many processors your computer has? One? Yeah? We agree on that, right? 100%. Okay. So you're right, it is one. However, each and every device that you connect might or might not also have a mini processor, okay? Which is called a special purpose processor. For example, the keyboard. Now the keyboard, because the keyboard doesn't want your computer processor to be busy with transferring the keystrokes to characters. Yeah.
Would a multi-core processor count as a multiprocessor, or is it just?
It counts as a multiprocessor, yeah. But we're gonna get to that, yes. Okay, so let's say your keyboard has a very small processor over there, just so it can translate the keystrokes to an actual characters and then send them to your device, right? So on different elements, they can be small mini processors that are doing just one specific task, okay? And this is done so the main processor of your device is not busy with things like this, okay? That are simple. Okay. Now, obviously, these days, nobody is using single processor systems like in 90s. We're all using multi-processor systems. And there are two main types, okay? So, they are asymmetric multiprocessors or symmetric multiprocessors. So, asymmetric means that each processor is assigned on a specific task. Let's say I have on my I'm watching a movie on my laptop while I am doing a project on Excel. So one processor will take care of the movie, another one will take care of Excel. Okay. These days, none of the computers we use are using this type of structure. All processors these days are symmetric, which means that if you have 5 processors and you watch a movie and you're using Excel, all the 5 are going to work on those 2 tasks in parallel or in a symmetric way. Okay? And actually, let me show you this here. Yes. Okay. So how is this going to work? You're going to have a memory, you know, this is going to be your RAM. All the processors will have access to this memory, and also every one of them can have a separate cache. About cache we're going to talk later. I know some of you are already familiar on what it is, but we'll cover it. So here's how it works. From the memory, each processor gets a specific task. It gets first to the cache, then it gets to the register where it actually gets executed and processed. Okay? This is how it works. Now, as my colleague told me, these days, of course, we were having just a single processor in every computer. But we developed a methodology that is called multi-core. So as you can see, when we're having a multi-core processor, this is still multiprocessing, right? The only difference is that we're having, let's say if we have 5 processors, instead of having 5 different chips, we're going to combine all of those chips into one. Now the question is, but why do we want only one chip now? Why don't we use the power of the 5 chips? Isn't that faster? Why do we need to combine them together? Why is that better? Any ideas? Yeah.
They're all more directly connected to each other.
Exactly. True. So when you're having 5 different chips, you need to have all the supporting electronics for 5 different chips. Okay? When you have one chip, you have 5 times less electronics. That might need to be more powerful, but they are 5 times less. Plus, as you said, it's way more easier to communicate. Of course, if I'm talking with you and we're in this room all together, you can hear me better, right? If some of you are in that building, some of you are in this building, another one in that building, you're not going to understand what I'm telling you, or it's going to take time, right? So for this reason, so the cores can communicate way faster, they are combined in a single chip. Have you seen a physical processor, how it looks like? Yeah? Who haven't seen? Okay, you're not gonna tell me, I know that, if you haven't seen. But let me...
My dad and I were working on the computer rig.
Oh, so you've seen... Yeah, if you worked on your computer, you know how it looks. But let me see. Let me just show you so you know how it looks. Okay, so it's actually nothing too interesting. This is exactly if you open a device, how it's going to look like. Okay. Yeah. So, yeah.
Like we have processor cores, right? CPU cores are all different ones.
You have a CPU cores.
No, like are both processor and cores.
Oh, you mean if you can actually see the cores or something like this? So you cannot see the cores, right? They're
Just like
built in.
I just want to confirm both. Like does processor contain cores or otherwise?
Yes, yes, exactly. So the processor, so in this chip, right? If this is a processor, all the cores are inside. Okay, so it's one chip. So if you open, let's say, a computer or any other device like a switch, router, those type of devices, you would see many small chips, right? And you're going to see one big one, okay, that has some markings on it. And normally, this is going to be your processor. Normally, it's the biggest chip on the motherboard. Okay, so in this chip, in the single chip, you have all of those cores. If you've seen in the past years since 2020, MacBook and Apple, they are building their own processors, right? Since 2020, they build their own processors, and every year they are increasing the cores. Like, I think now they have 16, 32 cores, 64 cores.
So based on number of cores, processor will be faster.
Will be faster, yes, yes. And also, when they're increasing the cores, also the size increases. So, you know, Apple, for example, every year they are doing like a big presentation about their products. And you can see, for example, the previous year chip was this big, and then the next year is like way bigger, just because they added more cores.
We can only make things so small right now.
Yeah, exactly.
The bigger it gets.
Yes, true. Of course, there is certain limit, right? So why don't we then build systems with 1 million cores? Isn't that going to be faster?
The amount of power that would take is one single component and the size it would be.
Yeah, first of all, the amount of power. Second thing is amount of heat that will get generated. So you need a better cooling system. The third thing, for which there is a limit, is that the more cores you have, the more inefficient each core is. Okay, so let's say if one chip is able to produce, let's say, X power, or let's say one chip is able to process 10 programs, or one core is able to process 10 programs. This doesn't mean that when you have 10 cores, you're going to be able to process 100 programs. Because, of course, you need more energy, a little bit more electronics for each core, right? So let's say with 10 cores, you might be able to process something like 90 programs, right? So you get more and more inefficient the more cores there are, but you still get improvement in performance.
Diminishing returns.
Yeah, and this is why it's very important things like heat management, how the motherboard is created. Those are things that are very important for the performance of the core. So let's say if you build a chip, but you don't have, even if you build the best chip, but you don't have the best cooling system or the best electronics, you might see a great parameters, but then when you use it, it's not going to be good. Or you're going to use it for 1 hour and then it's going to overheat, right? Okay, so other than multiprocessor systems, there is also other type of computing. So for example, if we really need like a lot of power, you know, they're supercomputers, right? That they have like enormous power, they can process very, very complex tasks. Obviously, this cannot be done by one processor, right? Or just one device. So for that reason, you have clustered systems. And cluster systems, it's very simple. So you have multiple devices that are communicating with each other, okay? And you can send a task to them and they can complete this task together, okay? Those devices might have completely different motherboards, completely different hardware, but they are going to work on the task together if they need to. And of course, in here, in the same way, we're having asymmetric clustering, which every device can work in a task, or certain device can work, other devices, they can stay on standby, okay? Or we can have symmetric clustering, where all the devices are working on the same task, okay? I don't know if, does Fitchburg have supercomputer, do you know? No? Okay. No? Okay. So in the past, when I was studying in one of my previous universities, we were doing a lot of aerospace things there. I was studying aerospace engineering there. So in aerospace, you need to really care a lot about aerodynamics, okay? So there are classes where you study aerodynamics, how the flow is moving. So if you want to simulate aerodynamics, it's very difficult because you need to predict each particle where it goes. And for these tasks, there is no way to do it accurately. For example, those big companies like Airbus, Boeing, NASA, SpaceX, right? In order for them to be able to predict what is going to happen with a spaceship, they need supercomputer that is going to be there of cluster systems, or also there's other ways like we're going to talk about cloud computing as well. But that way, for example, you can send your project for them to process it, you know, and after that, they're returning you the result. So something that for you might take you, let's say, 2 years for your computer to execute, the cluster system can do it in 1 hour, let's say, okay? And this is really something that allows us to process very, very complicated information very quickly, because the device can communicate. Another example, and I have friends that work there, is for Formula One cars. Formula One cars, they are having very, very big buildings just with computers because they want to predict how the flow is going around the car, okay? This is something that they really invest a lot on. Okay, and this is just a very simple diagram on how this works. So you're going to have a storage area where all the information is stored, something like a solid-state disk or combination of many solid-state disks. And then all of this information or the programs will get distributed to the computers, and then they can interact between themselves. Okay, this interaction is actually not simple because they need to know, each computer needs to know on what task should work and what part of the task is completed. Okay, so obviously the processor needs to be able to do multi-programming. So as we said, in order for the processor to be able to work with many programs at the same time, okay, you should screw the door? Okay. It needs to always takes and removes programs from itself. So let's say on your computer there might be 100 programs working at the same time. Okay, the registers are not that many to process all the programs. So when we're designing an operating system, it should be able to put for execution a specific program, and while this program is waiting, to stop sending bits to the processor and send to the registers other bits from another program. Okay, and this is what is called job scheduling. Okay, so this is something that is done in the background, and of course we're going to cover this as well. Now, time sharing is when where multiple users are using the same device. For example, at work, you're working on a system that multiple engineers are working on this system, right? And the operating system there, for example, let's say we're using Linux, we want multiple people to be able to go there, interact with the terminal, and do different tasks. And for each user, the experience should be as this user is using the system only by himself. Okay? And this is why when we build operating system, we need to build it in a way, if it's for that purpose, to be able to be accessed from multiple people at the same time. Okay? And this is called time sharing. So there are some requirements, of course. We need to make sure the response times are less than 1 second. Okay? Of course, so we can also have a virtual memory. For example, if some user is demanding too much data, this system can be also connected with the cloud where there is additional memory, and we can just allocate some of the tasks to that memory. Okay? Okay, so yeah, this is a very simplified way of how to do multi-programming. So let's say if in the memory we have 512 megabytes, which those days is more like 16 gigabytes, bless you, or more, you just stack the jobs one over the other. And of course, if you have too many jobs at the same time, then you start slowing down and jobs start getting dropped. Okay, so yeah, we covered this already. The operating system is interrupt driven. We already talked about the exceptions and the traps. Okay, let me see some. Yeah, let's continue. Okay. Okay, that's important, yes. Okay, so here is the thing. As we already mentioned, inside the operating system we have the kernel, that is the core, and we also have the other programs, right? So most of the operating systems, they work in two modes, as I mentioned previously. So they work in user mode and kernel mode. Okay, and because we already talked about it, what is usually running in user mode. So when are we in user mode? When we are executing what? Yes, yeah. Yeah, exactly. When we're running applications, we're in user mode. Okay? Yep.
Things that require like user interface, something like that. Or
That are, sorry?
that are like connected or require like user interface or input.
Yeah, yeah, of course. Yeah. Yeah, some specific tasks to the user, of course. And when we're in kernel mode, we're actually making changes to our system. Okay? So, as I said, if a user runs a program, the user always starts running the program from user mode, and then if this program needs to access something from the kernel, then it switches to a kernel mode for a little bit, it gets this information, and then we go back again to user mode. And as I said, this is done for the only reason so the operating system is protected from outside threats. Before it was actually not like this. You probably recognize that recently in the past, let's say 10-15 years, people start getting less and less worried about computer viruses. And those of you, I mean, I'm not that old, but those of you that are like similar to my age, for example, when I was a kid, your computer will get viruses like all the time. So I don't know, I'm 29 by the way, soon 30, but when I remember maybe around up to 2010, something like this, the operating systems were always like you could click something on the internet and then straight away you could get a virus in your device and then you have to reinstall the operating system. These days we're not getting this too much, and the reason is, first of all, the kernel is way better protected. We don't allow any external access to the kernel, okay, by default. And also in the internet we have firewalls, which is another topic, okay? So those are the reasons. We can actually have more modes. For example, if you're running virtual machines, okay, you can have additional modes for the different users. But we're going to talk, do you know what is virtual machine? Why would you need virtual machine, by the way? Why?
Like, to be secure. Just to operate remotely.
To operate remotely, to be secure, yes, both. Okay, anything?
While working on the projects, like we will be given VDS, virtual device.
Yes, yeah. Sorry, say again? Yes, exactly, also. Yes, true.
Security concerns.
Yes,
So this can't. Resource augmentation.
exactly. So you're all correct. So we would use virtual machines, for example, if I don't want my computer to get involved in anything related to the project I'm doing, I can just have a virtual machine, which is an OS that is running within my OS, okay, or an OS that I access remotely from somewhere else. So I get access to this virtual machine and I run all the programs there, okay? Yes.
Like how all of these computers work, that all run off of
Yes, yes, yeah, exactly. So yeah, I don't see actually any computers there, right? So they just access the, they just run remotely, so they get the data from the main server where it has enough memory, plenty of memory for all of you guys, and you're just accessing it. Yeah, exactly. All right. Okay, and here is displayed what I was talking about. So, for example, if you have a user process, okay, what is going to happen is at some point you might need a kernel, so you're going to do a system call, and the system call is just changing something called the mode bit. So obviously, if you have two modes, how many bits you need to do this operation? It's a tricky question. So I have a bit or bits that is going to, this bit is going to decide how many modes I have. So if I have 2 modes, how many bits do I need to show that? To show
This token, so you need one. One is a
1? 1? What do you think? Is it 1?
one.
Yeah, it is 1. Obviously, you can represent it just with 1 bit, and this bit can be 0 for, so in this case it's for the kernel mode, is 0, and then if you want to go to user mode, we just turn the bit to 1. If we have 3 modes, how many bits do we need to represent them? 2 bits, yeah, exactly. Okay, so now, the next thing we're going to briefly talk about is actually are 2 very important terms that we need to make a difference between them. The program and process, okay? So you can use a slide. What is a program?
Program. Set of instructions.
Sequence of instructions.
Sequence, yeah, exactly. And what is a process?
Sequence of programs. Sequence of running the program.
Sequence of running the program.
Lightweight thread.
Say again, sorry?
Lightweight thread. Thread is nothing but a like task inside a task.
Okay, yes, close, close. But there is like very simple expression of what process is actually. Can you think of a process?
It can define as processors, thread.
Series of steps.
Yes, but wait a second. So program is instructions, which instruction is a series of steps, and process is a series of steps. So what's the difference between them then? So yes,
My immediate thought was that it's a program.
6 of programs. Well, a program, a process can be part of program, right? So you cannot define process with program. It's even, but yes, you're half correct. Okay, so a process is just a program that is currently, so process is a program, you know, program is sets of instructions, so that is currently running in your computer, okay? So let's say you have a program set of instructions, right? So when you run this set of instructions in the CPU, then you have a process, okay? So this is why you can see here that program is passive entity. So program is something that is not running, while a process is a program that is currently running, okay? And it's in the background, so you have a process in your device, okay? So let's say if I write a code that is saying while true, print hi. So this code itself is a program. But when I run it, it will run constantly in my computer, so it will become a process. Exactly. Okay, good. So yeah, I'm explaining this because it's very important to do the difference, especially when you work with operating systems. So I hope it's clear now a little bit more. Okay. Okay, so here I just started what a process can do, right? So obviously process can create and delete systems and processes, right? Okay, so also we can suspend or resume process, okay? We can synchronize processes, we can communicate, establish communications between different processes. Those are all things that processes are doing. They're not simply running something that you see, but they're also communicating between each other. Okay, you can imagine them as separate people. They're communicating. Some people enter the room, some people exit the room. They're interacting. They are gaining knowledge from each other. They exchange data. This is what processes do in the background. Okay. Okay, so this one we already covered it. How to manage the memory. Obviously, we have to keep track on all the parts of the memory that are used. As I said, yeah,
So you take it down.
the previous slide, or
I'm just asking a question about.
oh, okay, yeah,
So in reference to Windows, would I be correct to say task in Windows is a process?
yeah, exactly, exactly. A task can be combination of multiple processes interacting with each other, okay? And when they work together, they can complete a task. So, for example, you have the what's it called, a task manager, or the in MacBook is activity monitor, right? Uh, so both of those, for example, they're showing the different tasks, and sometimes you can open them, right, and see what process are running within them. Okay, so yeah, the task manager exactly is showing like all the tasks and the processes in your device. Okay.
Parallel tasks on Facebook.
Yes. Yes. Yeah. Okay. So storage. Now, how is the storage managed? So mainly the storage in our devices is managed by files. Okay, so obviously you don't just see a set of bits, but you see different files with with information, and those files interact together. You can even take the files as the instructions, right, as the program. So one program is combination of multiple files, okay, and when you run this program, so you store this program in the memory, in the storage, right? And when you run this program, it becomes a process. So the file system that you have, you know, instead of having a bytes, it's way more readable, of course, to have files. So this is how we do it. Okay, I want to show you that. So here I just listed, and actually you're going to have those presentations. So that's why I included tables like this if you're just interested to look in your free time. So right here you can see that all the different types of storages that are possible in your device. So you can see from the magnetic disks, okay, to the register, which are the fastest. So you can see the registers usually have about 1 kilobyte of memory. So it's very low memory, but they are, as you can see, the bandwidth is a lot, okay? So this means they are very fast. Does any one of you know what bandwidth is? Yeah.
It's so it's the rate of data transfer through megabytes.
The weight or
The speed.
the speed? Yes. So when you have more bandwidth, you have more speed. Yeah.
Capacity of.
Capacity, yes. Capacity, yes. True. So yeah, you're correct. Now, bandwidth, as you can see, either you can describe it for digital data, you can also describe it for signals. So for example, when we talk about signals, okay, if you have, let's say if a signal has frequencies between 0 and 1000 hertz, this means that we can use a lot of different frequencies. So we can use the frequency of 1 hertz, 2 hertz, 3 hertz, and so on. So this means it can carry a lot of information and gets transferred to the air, right? In the computers is the same. And actually, I don't know if some of you is in my data communications class as well, but if not, there exactly we're talking about the bandwidth and how the analog bandwidth is related to the digital bandwidth. So yeah, the more bandwidth we have, the more information we can carry, okay? So for this reason, the registers, they have the most bandwidth, which means that they can process information very fast, so megabits per second, okay? So they can process 20 to 100,000 megabits per second, which is exactly like you say the speed. And obviously, the more we go to the left, the lower speed it becomes, but we have more storage. Okay, as you can see, the cache is the second highest speed comparing to the rest of the memories. And we'll talk about it soon. Okay, so who can tell me what is caching and what is the cache? Any ideas?
Cache is like stored memory, which is
Mm-hmm. Okay, yes, it's memory that's storing. Yeah, you were saying? Say again.
Browsing data.
So say.
Browser, like whatever we perform on the
Okay.
browser, that will be stored by the cache, I think so.
Okay, good.
basis search history,
Yeah.
fields that will be
Yes.
automatically stored in the server.
Mm-hmm.
That might like
Previous stores are like, this can store like that, magic can store.
Yes.
might
So
be used, in future giving some kind of suggestions.
Solutions, yeah.
For example, like
right.
if you draw something in Amazon, Facebook,
Okay.
products, so we'll be giving suggestions, reporting.
Segregate the things like
Yes.
and that's
Yeah. So for example, of course, and I'm not surprised, you're the most familiar with.
Like in simple terms, we can say like it stores browsing history.
Yes. So we store some information there. Yeah. Exactly. Yeah.
Generally, cache is used to store better results that
Okay.
have performed before, but
Yes.
are frequently requested.
Exactly. Yes.
Second
Yes.
one, when it's
Yes.
resources, instead
Yes.
of re-executing them, you actually retrieve them from them.
Yes, correct. Yeah, this is actually the closest explanation. Yes. So I'm not surprised that most of you know what cache is from accessing the internet. In the operating systems and in the hardware, it works exactly in the same way. So in the browser, yes, when you browse, you get cookies that are getting saved on your browser. Okay. Another way of caching when you're using the internet, for example, if you're accessing a website very often, it gets stored for you on a server that is closer to you, not on your device, but on a server that is closer to you. In fact,
Netflix has a caching like
of course, yes, of course, yeah.
What is the difference between cache and the cookies?
cookies like
Cookies in your device always, right?
Cache's data will be stored in server.
Yes. So
it will store if you allow it will be stored. If it doesn't allow, doesn't store your random section.
yeah, and cookies. So the cookies are stored on your device, and they're used, for example, when you do a request to the server. So let's say you want to access a website. When you do a request, this cookie is getting put in your request and is getting sent to the server. Okay? Yes. Yes, exactly. And they are unique for you, right? Okay, but this is also type of caching because you're storing certain information. But for example, to my point, when you, for example, people in Fitchburg, let's say they access certain website way more often than people from another area, then this website for you is going to get downloaded with the information on server that is close to you. And then next time when you want to access it, you're not going to access it from the server that's in Texas. You're going to access it from a server that is close to Massachusetts. And for you, it's going to be way more faster to access it. Okay, so we deviated a little bit from operating system. But now, since you all understand caching, then you will get that very easily. So when a process is very commonly used, when a program is very commonly used, it is getting stored in the cache, okay, but not in the main memory. And why is that done? Because the cache is way faster than the main memory, and this makes your computer way faster. So for that reason, you're going to put it there. Sorry, say again? Yeah, after a certain amount of time, the cache is deleted. Correct. Yes, exactly. And the important part is it gets deleted because it also needs to be updated. You cannot store there, for example, information that is too old. In operating systems, and also, yeah.
So why it's suggested that if your computer begins to run slow, you may want to check if your cache is being cleared
Yeah.
correctly, because if it gets too full, then it can't store new things, and then it can't get faster and keep using it.
Yes. Correct. Exactly. So yeah, when you delete the cache, your computer might get faster because you might have programs in the cache that are not currently used, right? So in the operating system, always this somebody okay. Always when a program gets executed in the register, especially if it gets executed often, first it goes into the cache, and from the cache it goes to the hardware register. Okay, so then next time when we request some program to run, first of all the register is going to call the cache, is going to check, hey, do you have this program? Yes, okay, let's go. And that way you can see that it works way faster. Now, if it doesn't have the program, it's going to check the cache, then it's going to check the main memory, then, oh well, we don't have it in the main memory, we're gonna get it from the hard disk or from the SSD. Okay, so this is how it works. Okay, so I'll just say a few words for this one. So, as we said, the operating system, the most important thing there is to be secure. So there are two terms that we can define here, protection and security. So protection means that we are preventing from external threats to go into our operating system. Security means that we prevent also from internal threats. So for example, if in some way a program is able to actually access the kernel, as I said, we need to have those mechanisms to handle errors, with exceptions, and other software that is able to actually terminate wherever we get within the operating system, which these days, as I said, they are very sophisticated. Of course, always the best way to prevent something is to isolate it. So, for example, actually in our operating system, we're having user IDs, so certain users can do certain things, certain users cannot. In Linux, if you're a super user, you can actually change the system files, okay? If you're not a super user, you cannot do anything, you cannot change the system files. There are also situations where a file created from a user can be only modified by the specific users. We can also make our system working like this. And if the file, of course, is not created, nobody else can edit it. So what I'm trying to say here is that the best way of security, especially in operating systems, is to prevent access to information. Because if somebody has access, there is always a way to do harm. Okay, so just briefly, a discussion about what are the different data types that are used in, yeah, thank you, in the operating systems, okay? So we're having linked lists. Are you familiar with linked lists already, right? Of course, yeah. So you know what is single linked list, double linked list, and circular linked list, right? So a single one, you can imagine that you have a piece of data that points to the next one. Yeah, that points to the next one. Double linked list is we point to the next data, but the next data is pointing back to us. Which class did you learn that from?
Which class?
Did you learn this from Fishberg?
No.
Yeah.
Yeah? No?
Natasha's class.
Natasha, right? Yes, yes. I was expecting to hear her name because I think she's having a class advanced programming or something like this or something else.
I have
Which one you have?
computation with her tomorrow.
Which one?
Theory of computation.
Oh, theory of computation, yes. Yeah, so in Natasha class, you are actually going to learn linked lists, right? How to use them. So, say again, sorry?
She hasn't opened the blackboard yet.
Oh, she has opened the blackboard. Okay, okay. Well, yeah, that's not very good, but you see from her, you're going to learn a lot of things.
Oh, I got my bachelor's here.
Oh, you got. Oh, so you are already familiar with Natasha. Okay, so if you took Natasha class, probably you already heard about binary search trees, right? So, for those of you that, of course, haven't been, just very briefly, a binary search tree is a tree that you can find elements. Guys, I know you're excited. What are you discussing? Are you discussing about? Okay. Good, good. No, I saw that's good. It's good to discuss the things from the class. I like that. Okay, so in the binary search trees, okay, who can explain them because you already know them? So who can explain? Okay, let's go. What is very simple?
So that is the root node. 17 is the root node.
Okay.
It has two childs, 12 and 35.
Okay, so if I want to add a number here, let's say if I want to add a number 5, let's say we have just 17. Where is going? Left or right? Left? Okay.
We have different type of tree structures like based on activity.
Yes, yes. Yeah,
We have
exactly. So the smaller numbers go on the left, larger on the right. If I send something that is between, that is more than 12, it's gonna go here, and so on. So you can see that those structures, you don't just learn them just so you know them and they are not used anywhere. They are actually used in the operating systems because when we're building software, and especially when we work with the hardware, what we want always is the shortest path to find an element, okay? And those algorithms, they prove themselves that with them you can actually find a number or a value in a very quick way. That's why they're used, and that's why you're studying them. Okay, also hash functions, obviously, you know, you're having keys and values. So when you request the key, you're getting the specific value. This is also used in operating systems because it is very easy to find elements, right? So you can use an address of a program, and by this address, you can find the program, you can find the instructions, load it into the register, and run it. Okay. Okay, so different systems that we're going to discuss now. Is somebody familiar on what client server is and how it works? This type of connection? No? More or less, like a little bit you heard about it, you know, here and there things. Okay. So yeah. In the computer systems, there are different ways, of course, for communication. And in the client server way, actually, this is the most popular way to access data over a network. Okay, so we're having the client, for example, you're the client with your device that you want to access information. So what you do, let's say there is a server right here. So the server is the one that is providing the information. The client, as you can see from the name, is the one that is requesting an information. Okay, so how it works, you're going to send a request to the server, okay, and if the server has this information, it will give you a response with the information you need. Okay, all web applications, websites that you access, they're only client server based. Okay, you always request information and you get it. Pretty much that's it. Of course, you can even build client-server applications on your computer. You can create a very simple Python code that is the client, very simple the server. Have we done something like this?
last semester, yeah.
Yes. So last semester what we built was one program that is the client, one that is the server, and then the client requests certain things from the server and you get it, yes. So yeah, this is how it works. Okay, so despite the client-server methodology, there is, and this is used by some applications these days, there is also peer-to-peer environment. Okay, so peer-to-peer means that all the clients, they are connected via internet. For example, did I put here Skype? Yeah. So for example, if you ever used Skype, this is how Skype works. Okay. This is actually different from some of the other communication applications that you're using. In Skype, over the network, your traffic don't go through a specific server, but the clients just communicate between themselves. These days, always, for example, let's say if you access Facebook or Messenger and you text with somebody, right? So your message gets to the Facebook server, and from there it goes to the person. In Skype was not like this. You're connected over the network, and only you two can exchange the messages. So when I send you a message, right? I'm the server, and you're the client, right? You request a message from me, I give it to you. So all the clients, they can be their client or a server in that methodology. All right, so since we talked about client-server communication, it's also worth it just to mention briefly how cloud computing works. Okay, have somebody of you ever uploaded anything on the cloud? Yeah. Actually, I think that all of you have done it, right? Especially if you've sent projects to each other.
I was going to say, even if you don't know, you did it.
Exactly. Even if you don't know, you probably did it. So if you send something to somebody else, and this thing is not saved on this other person device automatically, but you can access it from this specific application. So the
Elaborate cloud computing, like what does it mean? Why we use cloud?
yeah, I will say in a second. Yeah. So as I said, you might use cloud even if you don't know that you did when using all the communication applications. Now, why would we do cloud computing? Because it is very simple and very easy. Like I can start a company immediately from my laptop, and I can create all the software, and my laptop can be very bad. I can just do everything on the cloud. Okay? So on the cloud, you can see you're having public, private, and hybrid clouds. Okay? The public clouds are those that everybody can access, just like we mentioned with the social network. Okay? Private clouds is somebody that you own or some company owns, and hybrid can be either or. Okay?
Like cloud means you store data virtually, or you
Yeah.
store data in virtual machines.
Yes.
Uh,
Also, it can be, you can connect with anyone through actually with the access of internet.
Yes. So cloud can store data, but can also be used to execute data.
And
Okay?
also it is auto scalable.
It's exactly. So
Like
yeah.
it's a virtual machine only.
Yes.
It's like a
Yeah.
virtual storage, something like that.
Yes, so it can be storage, but I would also say that it is storage, but it is also way more than storage. Would you agree with me?
It's just a part of it.
Yes,
It's like a software as a service.
exactly. So, yeah, and we have it here, right? So you see that we can have software as a service, platform as a service, okay, or infrastructure as a service. So in cloud, okay, you can have, first of all, storage as a service, right? This is the last one, okay? So you can use infrastructure. So very big databases in which you can save plenty of information, and that's it, right? But also you can have more than this. You can have applications with which you can build software, okay? Yes, yes. AWS, Azure, say something else.
GCP, Google Cloud.
Yeah, also Google Cloud, exactly. Yeah. Yes, yes. So the Microsoft Cloud is Azure. Yeah, correct. Okay, so yeah, there you're getting like so many applications with which you can really build wherever you want. Okay, so you're going to use their platform to do things. Okay, and finally, which is my favorite one, software as a service.
VDI also becomes one of the cloud application.
Say again, sorry.
VDI, virtual
Virtual desktop. Virtual server.
VDI.
Oh, a virtual server.
Software as a service.
Yes, this exactly. This is a software as a service.
Also cloud. So you have like
Yeah. So I will give you.
physical device, we use like cloud.
Yeah. So instead of using physical device, instead of purchasing a lot of hardware, what we can do is just use, let's say, Amazon EC2, and they have many other type of technologies there. Yeah. Yes. Yes. Exactly. Yep.
In a way, it's like instead of having the program for like Microsoft Word
Yep.
directly on your computer, you are rather like calling the cloud to
Yeah.
provide you access to Microsoft Word from Azure.
Yes, yes. Or you can work directly on the Microsoft cloud. For example, so in Fishberg we're using Gmail, right? Okay. So let's say in your drive with Google, with the Google Cloud, you can actually use an alternative of Excel. I forgot how it was. Google Sheets or something like this, right? Okay. Yes. So you can use Google Sheets and you can work directly on Google Sheets on the Google Drive. You don't need to do anything on your device, right? So you're using their platform. The same you can do to build applications, right? Some different software that builds applications. Now, software as a service is what is actually how you can actually deploy programs that everybody can use. Okay, so this means, for example, I can create a program on Python, I can deploy it on Azure. Okay, yeah, and then every user around the world can use it. I can also add a payment method. Who has been in my AI class before? Were you in the AI class, guys, or were you in the data communication? You were in data communications. Yeah. Sorry? No, no, I'm talking about which class you were before. Data communications or all of you, right? Okay. So yeah, yeah, it's true. Okay, so software as a service, you can deploy your software on Azure, as I said. You can add a payment method there, so everybody that is using your software pays you money for using your software. Okay, your software can collect the data, which is also stored on the cloud. Pretty much all the life cycle of your program can stay there, and this is how you can provide a service to somebody else, right? So software as a service is pretty much everything that you can access through the internet as a service, right? So popular libraries with which you can build software as a service are, for example, if you're interested in Python. Sorry, say again. Virtual what?
Virtual VDI.
Oh, yeah, of course, you can use virtual machines that are also on the cloud, exactly. But if you want to build application yourself, you can use tools like Django, Flask. Those are very popular tools on Python with which you can build web applications, then deploy them on the cloud, and you just created a software as a service that everybody can use. Okay? Okay. And finally, just so you don't think that the operating systems are just related to clouds or to computers, the operating systems are also, and this is a very, very big part of development of operating systems, for embedded systems. So who can tell me? Guys, can you tell me what embedded system is?
What is system?
Embedded system, yeah.
It's like
Okay, over there, embedded system. What is that? There, if you search jobs, sometimes
They're built in a larger scale actually.
larger scale.
Scale like the servers.
Okay, servers. Say again, sorry.
Only usable in, usable in networking, sir.
Okay, good. Yeah. Any other? Can you mention me like an embedded system, for example, that is not related to computer, but is something else?
on the software softwares that are being used in cars.
Okay.
Maybe there is not a operating system.
Okay, good. So, uh,
Like some devices which are made to do only a specific task.
close.
Like washing machines.
Like what? Sorry?
Washing machines.
Washing machines? Yes. This embedded. Yes.
Like our electric
Cars.
home appliances.
Cars are embedded system, right?
Yes.
Okay. So pretty much everything that has a computing power but is not computer, it's some machine that is doing something. For this type of machine, if you create a software, this means you're creating a software for embedded system. Okay? So this, say again, sorry?
Like gaming consoles.
Yeah, yeah. So sometimes when you search for jobs and they write in the posting, okay, I want the person is going to be working on embedded systems, like, and you're thinking like, what is that? So guys, have you, for example, seen like job posts where they write, we need experience with embedded systems? Yeah, or the person that is going to be hired, he's going to work on embedded systems. Yeah.
Basically just means you need to be able to work with the computing processes or something that's not really
Yes. Yeah. So because there are many companies that are building specific devices. Like for example, in the company I work for, we're building medical instrumentations. Those instrumentations, they have a computer behind the door, right? And this computer should work automatically. It doesn't have a screen, nothing like this, but it controls the whole device. Okay. So for example, when you press a button, many processes inside are happening that are decided by the internal computer. So this is what embedded system is. And depending on the different type of device, the embedded system will have different type of operating system. For example, if you're building software for cars, you're not gonna use Windows on the car, okay? You're going to create specific operating system that is going to manage the car.
Actually, the whole concept.
Yeah, yeah, exactly. Exactly. So how the process, let's say, we're gonna take the example with a car. How the process for building software for a car is working. So firstly, you have the car. You have the mechanical, so they are the mechanical engineers, electrical engineers, software engineers. Mechanical engineers, they design mechanical parts, electrical, they design everything related to electricity, how to move the parts and so on. And the software engineers, what they do, first of all, they decide how the motherboard, actually this is decided, so the motherboard is decided by the electrical engineers. So they decide what processor are we going to use, how we're going to design the whole system, right? Then once we have that, the software engineers, they need to figure out, okay, I have the processor CPU 3K something, right? They know what hardware they are going to use, and now based on this hardware they have and based on the device that this hardware is going to control, they need to create operating system that is doing this specific task, let's say for the car, right? And this happens in the background. They will create their own bootloader program that is going to boot the operating system, and then they are going to create operating system with built-in functions to move the wheels, to, for example, when you press the gas like too much, not to raise the RPM to the maximum, but to have some control over it, control the sport mode of the car or the normal mode, this type of stuff, okay? So this is in very simple words how operating system can be implemented in embedded systems, which I think is good to know because I think many jobs out there requiring knowledge with implementing. Yes, exactly.